This topic is called Solving an Equation with Radicals, Problem Type 4. So as you can see, Alex has several different problem types where you're solving equations with radicals, and this one is, I believe, the most advanced. What this problem requires is just carefully dealing with what I call your special forms. And I'll get to that here in just a minute. But to follow the procedure for solving an equation with radicals, we must first identify the fact that there are two terms on the left and one term on the right-hand side of this equation. So to get started, we have to isolate a radical term. Well, on the left-hand side, there are two radical terms. We need to move one of them to the right-hand side. It really doesn't matter which one. So what I would probably do is just go ahead and add the square root of x plus 31 to both sides. So if we do that, we have the square root of 5x plus 39 is equal to the square root of x plus 31. Notice that's positive once you've added that to both sides. And then plus 2. So we still have two terms now on the right-hand side. Now that we've done this, we employ the tool of squaring both sides of this equation. And this is one of the common places for errors. It is unacceptable and unallowable to square each term of any equation for that matter, but rather in this case we're going to square both sides. So you square the left side, you square the right side. Now this is potentially dangerous. That is an imperfect process, and what that means is we're going to be required to check any solutions we get at the end, and that's just part of the procedure for solving radical equations. So the nice thing about the left side, squaring a square root, that's going to be fairly straightforward. So squaring the square root of 5x plus 39 gives us 5x plus 39. That's the nice thing. That was in fact the point. It eliminated that radical. However, on the left-hand side, this is what I was referring to the special forms. We have these types of patterns come up over and over and over again in algebra, and they come up so often that we ask students to, quite frankly, just memorize them. A plus b quantity squared, you can write it out, and what it means is a plus b times a plus b. But and once you've done that, you can certainly use FOIL, but what we really want, quite honestly, is that you memorize that is a squared plus 2ab plus b squared. And as I said, that's a pattern that comes up so often in mathematics, we just commit it to memory. If you don't remember it, make yourself write it out and actually think about FOIL, and you'll get to this very same place. But what we tend to do, our prize for having this committed to memory, is we'll expand this out without really showing a whole lot of work. And this really tends to stump students in class when this happens. But again, it's a prize for knowing this special pattern. So following that pattern, we square the first term, so that just literally is x plus 31. Then you have twice the product of the two terms. So think about this. Think about multiplying this times 2, and that really doesn't do anything interesting other than say 2 times the square root of x plus 31, and then times 2 again. So that's why we're going to go ahead and write plus 4 times the square root of x plus 31. And now squaring that last term, which is just 2, that gives us plus 4. So this, turning into all of this, is really the key to the whole problem, quite frankly. I'll erase that funny highlighting to get it out of our way. So now we clean it up again. Notice what we've accomplished. Squaring both sides and doing that carefully, And legally, we have eliminated the radical from the left side. We didn't eliminate all the radicals, but we at least made progress. So now we want to do a little cleaning up. We have 5x plus 39 still on the left equals, looks like x plus 35 plus 4 square roots of x plus 31. Now, what are we going to do? Our next goal here is to isolate the radical term again. So that's going to involve focusing on these two terms, the x plus 35, subtracting them from both sides, excuse me, to get the radical term by itself. So I'm going to trust we can do that without too much hassle. We're subtracting x from both sides and subtracting 35 from both sides. So that's going to give us 4x plus, that's 39 minus 35, so plus 4 equals 4 times the square root of x plus 31. Now we have a good mathematical discussion. This will not happen all the time. So it's certainly not something you can count on, but it's worth discussing because it's certainly legal. At any point, you're allowed to divide both sides of an equation by a non-zero constant without causing yourself any headaches. So hopefully we can see that we can divide both sides by 4 right now. I'll point out that if you don't notice that, it's not going to be wrong to just simply square both sides right now. So I'll kind of talk this out both ways, but certainly it's going to make our lives a little bit easier if we notice that we're allowed to divide by 4 right now. So if I divide the right side by 4, that divides this away. Divide the left side by 4, that it's important to note that divides into each term. And where that gets us is, looks like just x plus 1 equals the square root of x plus 31. Now that we're to that point, I said I'd talk this out. If you didn't do this, and you just left it as 4x plus 4 is 4 times the square root of x plus 31. You square both sides right now. You will eventually get to the same place we're going to get here, but it's certainly, as you can see, a lot easier. So I'm not going to continue this path over here. I'll just say you could do it. And the only treachery here is recognizing the fact that you'd have to square the 4 and square the square root. So you actually have 16 and then times the quantity x plus 31 if you went with that path. But we're going to stick with the wiser plan over here on the left, and squaring out x plus 1. Again, I'll say back to our special pattern. There it is twice in this problem. It becomes significant. So you can either write that out, x plus 1, and think about just multiplication of binomials, or you can use the special pattern and be aware of how quickly you can call that x squared plus 2x plus 1. I'll give a warning. One of the most common errors here is to just simply square the x and square the 1 and just completely disregard the fact that you'd get a 2x in the middle here. So that's certainly a common place for a mistake. On the right hand side, we've squared both sides, or we squared that side, and that was the whole reason we did that, by the way, was to again eliminate that radical. That gets us x plus 31. Now look what we've done. We have actually cleaned this up to the point where we do not have any radicals, so we're making headway. We analyze this equation and realize that it is a quadratic equation, so our plan is going to be to move everything to the left-hand side. The quadratic equation, many times a good strategy is to isolate or to move all terms to one side to get 0 on the other side. So subtracting x from both sides, we'll have x squared. Subtracting x from both sides plus x. Subtracting 31 from both sides, we'll have minus 30 equals 0. And this one we can solve by factoring, so we'll go ahead and do that. If we factor the left side, that gives us x plus 6 and x minus 5. Setting each factor equal to 0 gives us x plus 6 equals 0, or x equals negative 6, and x minus 5 equals 0, or x equals 5. And now the important thing. Now that we've done all this work, we're not guaranteed that either of these solutions will actually check. The squaring of both sides as a procedure for solving equations is the only one that's an option here, but it is an imperfect process. So all that means is it's just simply a requirement, not a suggestion, to go ahead and check your answers and see if they are legitimate solutions. If they are, we circle them and move on. If not, they're called extraneous, and we X them out and don't include them in the solution set. And so when you check, you always want to check back in the original equation. So let's see if I can bounce up here and get that written down. So I'll write it right here so I can go down to C. That's square root 5x plus 39 minus square root x plus 31 equals 2. And most of this I'm going to trust you should be able to do in your head. And I'll kind of talk this out. In fact, I'll show you how to do this check this on your calculators. It's certainly a good idea. Simply, it's just substitution. So we're substituting in negative 6. So to check x equals negative 6, I'll go ahead and write that underneath here. If you substitute negative 6 in for x, that's going to give us negative 30 plus 39, so that's the square root of 9, minus negative 6 plus 31, so that's minus the square root of 25, and see if that's equal to 2, and I don't think it is. We're going to have a 3 here minus a 5 here, and that is not equal to 2. So the 6 does not work. So that solution is out. So to check 5, substituting 5 in for x in this equation, so that's a square root of 5 times 5 is 25, plus 39, that is what, 64, minus 5 plus 31, so that's a square root of 36, and is that equal to 2? Well, that is 8, minus that is 6, and that is equal to 2. So that is a solution. So as far as Alex is concerned, you're only going to enter x equals 5. The x equals 6 will not be a correct solution. So that's an important part of the process, checking your solutions when you're done. So there's a lot that happened here, but I'll just point out that 2 different times we needed to know this, and that is worth thinking about and worth spending some time on. So when we have solve for x, or x is a real number, that complicated radical equation came all the way down to x equals 5 was our only solution. That x equals negative 6 was extraneous, so we don't use it.